Hi, I'm Cheng Yang. I'm here to present our work JOCA, Task-Driven Joint Optimization of Camera Hardware and Adaptive Camera Control Algorithms. The designs of cameras are important to the performance of many intelligent systems, since the image qualities heavily influence the performance of perception tasks. Existing methods attempt to co-design camera hardware and the downstream task, and they have received improved task performance. However, cameras operate in varying capture conditions, so adaptive camera control algorithms are designed to control dynamic camera parameters to maintain image quality. The dynamic camera parameters are interconnected with hardware parameters, but they are often designed in isolation. In this work, we introduce JOCA, the first end-to-end framework that jointly optimizes camera hardware, adaptive camera control algorithms, and downstream tasks. We propose a hybrid optimization strategy, DF-grade, which integrates derivative-free and gradient-based method to train deep learning-based adaptive camera control algorithms under non-differentiable image effect rendering. We demonstrate camera design and camera control algorithms with improved performance under both standard and challenging conditions compared to prior method. Previous work has been proposed to co-design either camera hardware or adaptive control algorithms with the task. The methods that co-design camera hardware with the task assume fixed operation environments and ignores the dynamic parameters. Other works only jointly optimizes adaptive control algorithms, such as auto-exposure with the task, and most of them ignore some image effects induced by varying dynamic parameters. We tackle these issues by jointly optimize all three components, and propose a hybrid optimization method to learn the relationship between some image effects and dynamic parameters, such as exposure time and motion blur. In our framework, we use the camera with configurable hardware parameters to capture images from a scene. Then we adjust the images with the current dynamic parameters and add noise to the images. The dynamic parameters are predicted by the adaptive camera control algorithm at each time step, and the images are evaluated by the perception tasks. For optimization, we calculate a fitness function from the task performance to optimize the camera hardware using a derivative-free optimizer, and we use the loss function of the task to optimize the task model with a gradient-based optimizer. Finally, we optimize the adaptive camera control algorithm with the proposed DF-grade method. In this method, we perturb the predicted dynamic parameters by adding small perturbations. The perturbations are optimized with the fitness function from the task using the derivative-free optimizer. Then we use the L1 loss to drive the dynamic parameters to the perturbed values. The L1 loss is combined with the original task loss to update the adaptive camera control model. This combined method allows the algorithm to learn image effects that are rendered in non-differentiable manners. For image formation, we consider that the pixel intensity corresponds to the number of photons arriving at the pixel area during exposure time, scaled by the camera gain. We first calibrate the dataset images against the physical camera with known dynamic parameters. Then we scale the image with the predicted parameters by their ratios. We then apply the affine noise model to introduce noise to the images. We use the generalized form from tacos for different exposure settings and image sensors. We adopt and modify the architecture of the neural auto-exposure method as our adaptive camera control algorithm to predict exposure time and gain. We add a parameter awareness component that concatenates the dynamic parameter as a last step to the semantic feature branch to improve temporal consistency. In our experiments, we trace the object detection as a perception task. We use a pre-trained faster RCNN model and optimize with the ADAM-W optimizer. For adaptive camera control, we use the ADAM optimizer and training from scratch. For camera hardware and the perturbations of the dynamic camera parameters, we use a genetic algorithm following tacos. We use the average precision score as a fitting function of the perturbations, and we use average precision combined with a true positive ratio score for the camera hardware. The true positive ratio is computed as a true positive detection inside the camera's field of view against all ground truth objects in a 180-degree field of view. This metric prevents the camera from converging to a very small field of view. We compare our method against existing approaches, including using the task-specific adaptive camera control algorithm with off-the-shelf cameras and human design placements, as well as using task-specific camera hardware design method with a non-trainable adaptive camera control algorithm. We first evaluate all methods under a calibrated standard scenario with calibrated image noise and motion blur, and we additionally test under increased noise level for lower signal-to-noise ratios, representing a reduced average illumination or stronger sensor noise, and under stronger motion blur to represent faster motion. We first evaluate our method with synthetic images from the color simulator. For camera hardware, we optimize focal length, image sensor dimensions, pixel size, and camera placement. We treat the image sensor as categorical parameters and select it from an existing catalog. Result shows that under calibrated scenario, our method achieves sharper image by balancing exposure time and pixel size. With higher noise, the neural auto-exposure method learns to maximize exposure time and minimize gain to improve signal-to-noise ratio, but it cannot learn the relationship between motion blur and exposure time, as motion blur is rendered non-differentiably, resulting in strong motion blur in captured images. The average auto-exposure method fails to adapt to new signal-to-noise ratio and predicts similar exposure settings, whereas our method successfully learns to balance signal-to-noise ratio and resolution by balancing exposure time, gain, and pixel size. With higher motion blur, the neural auto-exposure method predicts similar exposure settings as the calibrated scenario and results in severe motion blur. Tacos with the average auto-exposure method reduces motion blur by giving a larger pixel size, but it sacrifices image resolution, whereas our method learns to give shorter exposure time for sharper captures with high resolution. We then evaluate our method with real-world images from the Waymo Open dataset. We only optimize image sensor dimensions pixel size due to pre-captured images. Again, we treat the image sensor as a categorical parameters as before. The results show similar trends as the synthetic image experiment. Our method produces high-quality images by balancing exposure time, gain, and pixel size. Quantitative results again prove that our method outperforms baseline methods under all scenarios, despite a smaller design space. Our ablation study demonstrates the effectiveness of our proposed DF-grade method and the benefits of jointly designed camera and the task. In conclusion, we propose a novel end-to-end method that jointly optimizes camera hardware, adaptive camera control algorithms, and perception tasks. We propose a hybrid optimization method, DF-grade, combining derivative-free and gradient-based optimizers to train neural network-based adaptive camera control algorithms under non-differentiable image effects rendering. JOCA outperforms existing isolated camera design and adaptive camera control method under both standard and challenging conditions. For future work, we plan to extend to more complex camera design problems involving unconventional cameras and multi-camera designs, as well as more challenging design scenarios involving adverse weather conditions. This research was supported in part through the NVIDIA Academic Grant Program. Thank you for watching, and please scan the QR code for our project page and code.